Um, this is just another Thursday evening stroll around our celestial neighborhood. I'm trying a fun new thing tonight. Um, the countdown. I'll see how it looks. It was a little shaky on this end, but thanks to Brian Levine for the suggestion. So um, just give another minute or so, a few more seconds for folks to join in. Um, Excited to have the YouTube back and running with this. So, yeah, I'm just gonna take a sip of my definitely non alcoholic beverage. and Yeah. Yeah. Let's get to it because I'm a little impatient and I'm just really excited tonight. So welcome everyone to your Thursday evening stroll around your celestial neighborhood. I'm Irene Peace, your friendly neighborhood astronomer. And one of the reasons I'm just really happy tonight is because I'm using a new system and not having to interface directly with Facebook. Yay! So this is me when I'm not dealing with Facebook. So tonight's topic was actually inspired last minute, as they often are, by something that happened on Monday. So, for those of you who tuned into Moontopia Extreme, the AAA live stream on Monday, there was a really interesting comment that I thought was worth thinking about a lot more about, like, well, do we consider atmospheres when we're measuring the sizes of worlds? And I said, I don't know, it seems like we should, and just kind of like took me down this little rabbit trail, which of course I didn't have time to get too far down because of grading and life and things. But we're gonna go explore just a little bit of that tonight. Before we go there, just want to mention the visuals that I'll be using. Usual, we have Stellarium, which you can find at stellarium.org, and of course, Open Space, which you can find and download for free at openspaceproject.com. So, to start off with, we'll look at a few things in the night sky in Stellarium, and we'll come back and look at sizes of things. So, night sky. Yes, totally clear tonight. So of course I'm stuck in Brooklyn. It's all good. It's all good. Not bitter at all. Um, so if we look over towards the west, there's some really exciting things happening in the west. Not like west like in Colorado. Like, well, the other day there was an eclipse out west, like in the Pacific West. But for tonight, really tomorrow night is what we want to look for. So if you want to practice tonight, go outside at the end of this live stream and look for Venus and Mercury, and you'll notice they're pretty stinking close together in the sky. Mercury had its greatest eastern elongation just a little while back, and so it's headed back west, going to come between us and the sun-ish, not exactly between us and the sun. The moon will be doing that. More on that later. But it's going to pass Venus actually tomorrow night. Whoa, look at that. Right smack dab next to each other. So that'll be a fun thing. You can see that, a little bit earlier in the evening. Let's like rewind back to about 8:30-ish, I believe tomorrow should be a good viewing time for that. So yeah, so if you look out in the sky around 8:30, you should see Venus. It's pretty bright up there. And maybe with binoculars, don't try it with binoculars before the sun is down. That can be a little bit dangerous. You don't want to risk looking at the sun directly. That will break your eye. So please don't do that. But once you see Venus, as it's getting a little bit darker, then you can see Mercury just to the left of it. So those will be a really nice view. And again, I'm expecting really fabulous shots from some of the astrophotographers out there. So looking forward to that. I don't know if it's actually supposed to be clear tomorrow night in Brooklyn, but yeah, someone can let us know in the chat, or you can, check the weather or just look outside at some point. The other thing, I guess celestial wise, as far as planetary alignments, blah, blah, blah. If you're a morning person, we have some morning things happening. The moon is going to be over by Jupiter and Saturn. So if you're up really early in the morning, like before sunrise, good for you. Um, but the moon is going to be over there for the next for just a couple days, from like around the 30th through the 2nd or so of June. So if you like seeing the moon by the planets, that's a fun thing. Again, if you're a morning person, I don't get up quite that early. That's seriously like before 5 o'clock in the morning. So pass on that. I'm saving up for the eclipse, which I think I'm going to do a whole thing about next week. Yeah, that's next week, because the week after is the partial eclipse. So the other really cool thing, though, this is your challenge, and I can't believe I almost missed it this year, because this is the time of year, especially for Northerners, we have a very limited window. What we want to be doing is looking for one of the, well, actually, yeah, probably the brightest globular clusters in the night sky. So you know how I feel about sparkly things, bright, sparkly things. So a few weeks ago now, I believe I've mentioned that, oh yeah, you can see Arcturus. Just turn on some constellation lines for a little bit of reference. So you can even try this tonight. But yeah, go ahead and keep trying this for the next week or two. Once it's dark, yeah, we need it to be dark. And you want to have a clear southern horizon. So actually, I think this mountain that's here might be in the way, but we'll figure it out. So you want to look for basically the bright star Spica, right? So we've talked about how you can follow the arc of the handle of the Big Dipper. You arc to Arcturus. It's kind of like this orangey yellowy star that's way up there in the sky. So you arc to Arcturus, and then you speed on to Spica. So Spica is going to be in the south in the early part of the evening after dark. And you don't want it to be like late. Like you basically want to catch Spica. This is the trick. You want to catch Spica when it's basically due south. So that's when it's at the highest part of the sky. It's crossing this invisible line in the sky that we call the meridian. It runs from due north to due south and passes through the zenith, which is the point straight overhead. So when Spica is actually just a little bit east, but we'll just say close to the meridian, it was just a little bit east of the meridian, when it's almost exactly due south, that's the time that we can look for this other fabulous thing that, dang nabbit, it's behind the mountain. All right. So I'm gonna I'm gonna go to the beach. Let's knew this was gonna happen. All right, so we're just gonna go to the beach. We go to the ocean. So if you go down to Coney Island, that part of Brooklyn, not the mountainy part by Mount Prospect. But yeah, if we go down to Coney Island and look way down by the horizon, there's, okay, not that. There's this blob in the sky that's Omega Centauri. Okay, and it's like not even picking it out. Here, let me, boom. Okay, yeah, Omega Centauri. So for all of those of you who are into like mapping and stuff, Omega Centauri has a very similar right ascension to Spica. So when Spica is clearing the meridian, that's when Omega Centauri is going to be highest. So if we just kind of like whiz through time here, even if we turn off the atmosphere, you can see that Omega Centauri never gets very high from this latitude. So again, in New York, we're like around 40 degrees north. So Omega Centauri just barely skims the horizon. So you really have to be able to see like all the way to the horizon. If we look at this, it's what? Altitude. It's all of, yeah, less than 2 degrees above the horizon. So maybe go down to like a little bit further south if you want to get, a better view of it. So it's just going to be skimming the horizon. It's not going to be above the horizon for very long. But this is one of the biggest, brightest globular clusters in our night sky. It's generally considered a southern object, but yes, it's technically above the horizon at our latitude. So that's kind of a fun challenge. If you're further south, it's definitely, visible to the naked eye. But I'm going to say from up here, you probably want like telescope or binoculars to help you pick out like this faint fuzzy thing that's just going to be like barely skimming the horizon. But definitely getting the timing, because again, you have a small window to catch it, and your kind of marker is when is Spica really high in the sky. Um, so if you find Spica, look right below Spica, due south when it's highest in the sky. Um, there you can find Omega Centauri. So that's a fun challenge. Go find a place with a clear southern horizon and see if you can pick out Omega Centauri either with binoculars or a telescope, or if you're further south, even with the naked eye. That'll be a fun thing. So, we will come back to Omega Centauri in a sense a little later, but for now, back to the open space and some spacey things. Space is big, really big. But you can read all about that in the Hitchhiker's Guide, which we talked about last time. But yeah, talking about huge things and big things and how huge is huge and what do we mean by hugeness. Um, I'm just gonna kind of stroll around here for a bit and really, when astronomers talk about how big things are, how huge things are, they might mean something a little bit different than what we would mean in just like everyday language. So, like, usually when we talk about how big things are, like in everyday language, we're talking about like volume, right? Like the radius, like the physical size of things, which astronomers talk about sometimes, but a lot of times they're talking about mass. So we'll get to mass in a little bit, but I thought we'd start off talking about like the physical size because that's kind of what brought this all up. Um, was talking about like, well, how do we figure out like the sizes of planets and things? Um, so So we'll kind of just poke in towards Mars. Um, so as far as like figuring out like the radius of the Earth, right? We basically measure from the center to the solid surface. So for rocky worlds, um, and so we like to say worlds because not just planets, but moons also. We generally measure to, yeah, the surface. But surfaces can be lumpy, right? I mean, just, look at Mars or the moon or any of these other like marvelous terrestrial worlds that we have in our solar system. And it's like they don't have like a nice, smooth, uniform surface. So, one, we don't measure their atmospheres. All right. So just know we don't count the atmosphere. That seems to be the general consensus. But we measure to kind of an average radius, a mean radius. So with the moon, or sorry, with Mars, that actually used to be based on, we used to measure like kind of like zero level on Mars, like we have sea level on Earth, but there's no oceans on Mars. So we would use like this zero datum based on atmospheric pressure, but now we actually use like an equipotential surface. It's based on like the mean radius at the equator. So the mean radius overall, we just set that at the equator. That's how we get like what would be sea level, a zero datum on Mars. But so there's some parts of the radius like that extend out further, like you have these huge mountains like Olympus Mons sticking like halfway out of the atmosphere, almost. And then you have like the deep canyons. But if we kind of like average that out, that's what we're going to use for radius for rocky worlds. And really this had the solid surface. I think for Earth that includes the water. Um, and also just keeping in mind that worlds tend to not be spherical, right? So all the stuff in space that's spinning, so planets, stars, moons, whatever, they're not really spherical. They're actually more like ellipsoidal and they're like a little bit pudgy in the middle. So they have equatorial radii and polar radii. And so we do actually often have those marked separately. Um, so usually the equatorial radius is going to be greater than the polar radius, but that's what we're going to be using for looking at the sizes of things. Um, if we pop over to something slightly different, wow, yeah, slightly different. So that's for rocky things. So even if they have an atmosphere like Earth or Titan, we're not going to count the atmosphere, which I feel like is a little bit cheating because Then when we talk about the giants, right? So we also have these gas giants and we have ice giants. So what about those? Like they have this atmosphere and they don't have like a solid surface per se. So what do we do about that? Like how are we going to figure out the radius for something if it doesn't have a solid surface? Um, so yeah, a little bit different, but kind of what we used to do on Mars. We just use that. We use the atmospheric pressure. So we'll use the distance from its center at which the pressure is 1 bar, basically one atmosphere. The pressure of the Earth's atmosphere at sea level on Earth, which sounds a little bit arbitrary, and frankly, it is. It's Earth centric, but hey, this is where we are. This is where we're measuring from. So deal with it. Um, but then the interesting thing is that like if you've seen like especially those pictures of like all the planets lined up between Earth and the moon, and they don't include like the extent of Saturn's rings. So the ring particles, those would really be considered satellites. So when we're talking about like the radius of Saturn, we're not including any of its satellites. So we're not including any of the rings or the ring particles. Um, so, yeah, so not all if you wanna consider, like, all of the atmospheres, you'd have to add that, but it's not gonna be too terribly much compared to, like, the bulk of these giant planets, either the gas giants or the ice giants. So yeah, so for rocky worlds, measuring kind of just the average distance from the center to the solid surface, not including any atmosphere. And then for the gaseous planets, gaseous worlds, we're measuring from the center to the location where the atmospheric pressure is a certain amount. That's kind of arbitrary, really. But then that begs the question, well, what if you have a rocky world like that has a higher atmospheric pressure at its surface, like Venus? Like if we were treating Venus like a giant planet, like one of the gas giants, then its surface would be like way up in its atmosphere. But I guess we don't. We just still consider its rocky surface. So Venus is kind of weird like that because I feel like it could go either way and you can make all kinds of arguments. Um, but don't at me. So just saying. Um, so yeah, so in the sense that a lot of this seems arbitrary, and yet it's actually very important in figuring out how big some of these things are, like what are their radii? Because if you read a lot of literature, which I'm sure you all do in all your spare time, um, then you'll know that astronomers like to, when we're looking at all these um, other star systems, other planetary systems, as we're finding like all these fabo exoplanets and things, we like to talk about them in terms of how big they are compared to Earth. So we'll talk about Earth radii and Jupiter radii, and even as my mother discovered, Neptune radii. Um, she called me one day, is like, "Is this a thing?" And I was like, "Yeah, Neptune measuring things in Neptunes is a thing apparently." Um, so so it is important to have a sense of like exactly what these measurements are if we're going to start measuring and using those as units to measure and quantify other worlds like beyond our own star system. So especially for like Jupiter and for Earth, and then also a little bit for the sun. So we measure things in solar radii, um, and we measure things in Jupiter radii and Jupiter masses and Earth radii and Earth masses. Um, and so at some point, the AAS, and again, those are, or sorry, yeah, actually, I think it was the AAS, not the IAU. I could be mixing that up, but I have the link so you can see it. Um, they basically said, "Hey, maybe we should standardize some of this stuff." And I think they decided not to actually vote on it, but here's the paper so you can read all about it yourself. Um, and people basically said, yeah, these things are changing, and we keep refining our distances as we're studying Jupiter, as we learn more about the Earth, and our systems of measurement, our methods of measurement get better. Like these numbers actually change, and that's a problem. So we're just going to pick these numbers and we're going to use this number as, our equatorial radius for Jupiter, and we're going to use this number for our polar radius for Jupiter. So then when we're talking about, some other world and we're measuring it in Jupiter radii, we can be very specific, and that amount isn't going to change as we refine our measurements of Jupiter itself. The other interesting thing there is that for the masses, because again, we also use Jupiter masses, Earth masses, solar masses, but they don't just use mass by itself. They use mass along with the universal gravitational constant, which apparently isn't as well known as we would like it to be. I mean, not to as many decimal places as we would like. So they kind of lump those together. But you can read all about that in the paper. But I did want to get to so those are some relatively straightforward things to measure compared to other stuff in the universe. So it's well, what about stars? So I guess we've looked at rocky worlds, we've looked at gassy worlds, gassy things. But even gassier, or I guess they're more plasma than gas, are stars. So how are we going to measure the distance or the radius of a star? Well, those are pretty well agreed upon. That's just going to be the distance from the center to the photosphere. So for those of you who do solar observing, which hopefully everyone will do some very safe solar observing in about 2 weeks when there's a solar eclipse, partial solar eclipse from New York City. That's basically where the photons escape from. So that's what we see when we look with visible light. So that's kind of like our edge. So the stars have lots of different layers. But then for the radius, we're basically measuring from the center to this photosphere. And again, there are, equatorial radii that are going to be greater than the polar radii because spinning things are pudgy. So what about things that are definitely not so spherical, so symmetric? So even though I said these aren't quite spherical, they're ellipsoidal or whatever, but they're still a lot more symmetric than other things I'm going to bring up a thing in the sky. What about big globs of gas? So if you have a big cloud of gas, like a giant molecular cloud, how do you measure the size of that? And that I don't really have a good answer for. I'm just going to say looking at relative density. So similar to the atmospheric pressure, just saying, oh, we're going to cut it off after the atmospheric pressure drops to a certain amount. So you get similar things, and you can measure the spectra, where does the spectra drop off? Where do you stop getting emissions or whatever? So what we're seeing now is basically an all sky image of what we would see if we could see just this one wavelength of light. So this is our H alpha. This is 656 nanometers. So the light that's given off by this one transition of hydrogen. And so this kind of helps us trace out some of these huge clouds of gas. And there's different types of clouds of gas, but these are just some of them, just one example of a type of cloud of gas. And so we have these that are mostly lurking in the disks of galaxies. For galaxies that have disks, we also see these in dwarf galaxies. But yeah, just kind of this question of how are we going to measure the dimensions of these clouds of gas? Well, you can look and see, you can kind of see the density drop off. And you can see the spectrum change as you're looking from one kind of along the edge of a cloud of gas. The other thing that I wanted to check in on, well, I guess 2 more things if I have time, of course, was the big pretty things. So globular clusters. How do we measure the size of a globular cluster? Because if you look at it, I mean, it's just a big ball of sparkle, right? And in the center, there's more sparkles, and on the edges, there's less sparkles. So globular clusters actually have 3 radii. 2 of them make a little bit of sense. And the third one is just very, very mathy. So it makes sense if you do lots of math and astronomy. So there's the core radius. That's where, if you look at the brightest part in the very center, that's the core, right? So you look at how bright that is, the luminosity, and you figure out where that luminosity drops off to half. So the brightest luminosity in the center, and then figure out where it's at half of that, and that's what we call the core radius. So that tells you kind of the sense of the core um, of the globular cluster. And then there's also the Jacobi or the tidal radius. That's basically going way out and looking at the extent of kind of the gravitational influence. So you say, all right, if I were a star this far away, would I be gravitationally bound, or would I easily get tugged away by some other passing thing in the galaxy, right? So core radius kind of giving us a sense of the inner densities of these globular clusters. And this is Omega Centauri, by the way, image from the European Space Observatory. Um, but yeah, so core radius and then the tidal radius or Jacobi radius. And there's also a half light radius, which is basically the geometric mean of the whole with half max along a semi-major or semi-minor axis. But yeah, mumble, hand wave. Anywho, so that's how we can find the radius or quantify the sizes, physical volumey sizes of just a few things in space. So we can see a lot of these things by looking, all right? Because again, oops, again, astronomers just gather light, right? So we can't like go and like bring our ruler up next to a planet or a globular cluster or what have you and measure it that way. Um, but we can look in our telescopes, and if we know how big one thing is, we can figure out how big the next thing is. We can figure out how far away something is and how big it looks, and based on that, figure out how big it actually is. But then what about like masses? So the big thing that astronomers are concerned with is not just like the physical size, like, how long, how wide is something, but a lot of times when they're talking about how big something is, how large it is, they're talking about its mass. Um, and fortunately, mass is relatively straightforward for calculating. And I just realized I forgot to make some of the orbit lines in here a bit brighter. Um, but we'll see how this goes. So coming up here on Jupiter, yeah, this gonna be really hard to see because I can barely see the lines as it is. So actually, what we'll do is we'll jump out to the sun. Just look at the sun. Um, and look at some of the orbits of the planets around the sun. So what we can do is actually look at an object in space. And if we can see things going around the object, then we can figure out the mass of the central object. This is based on one of Kepler's laws of planetary motion, saying that the square, I'm going to get this mixed up, square of the period is proportional to the cube of the semi-major axis. That is the time that it takes for an object to orbit the central body, like a moon to go around a planet, or a planet to go around the sun, or even a satellite to go around the Earth. I think I can... Nope, that's not it. That's definitely not it. That's gonna depend on the distance, right? So the semi-major axis, that's just the average distance, basically, we'll say, between the two objects, centers of mass. So by watching planets go around the sun, we can figure out the sun's mass. So that's that constant of proportionality between the square of the time and the cube of the distance, that depends on our universal gravitational constant, as well as the actual mass of that central body. So like the mass of the sun, Or if we watch Jupiter's moons go around it, that's how we can figure out the mass of Jupiter, by knowing how far away the moons are from Jupiter and by watching how long it takes them to go around. So we can do that really easily for things that have something orbiting them. If we look out further into space, we can also see things interacting gravitationally. So even like with galaxies, like we can find the masses of galaxies or estimate the masses of galaxies, not because two galaxies are necessarily orbiting around each other, but we can look at the interactions of like neighboring galaxies and kind of saying that like, oh, they seem to have like this much pull on each other, and just looking at gravitational interaction. So it's kind of funny that like we still use like gravity to find the mass of things, because that's how they interact. They still interact gravitationally based on their masses. Um, just want to make sure I've paused this. And as Brian had pointed out, yeah, Jupiter has one Jupiter mass. So that's how we know that Jupiter has one Jupiter mass. And we know what a Jupiter mass is by watching the Galilean moons. The sun has one solar mass. And it's funny, like when I was mentioning earlier that astronomers tend to talk more about the masses than like the volumes of things, because I know offhand, like the mass of the sun is about 2 times 10 to the 30 kilograms. I have no idea what its radius is. But these are the numbers that we store in our heads, more masses than radii. And I guess an extreme case of that would be, I don't really want to go there, but a black hole, right? It's like we don't even talk about the size of the black hole. You might talk about the size of its event horizon or some other feature, but really we talk about their masses. And we talk about like the mass gap of black holes. We're talking about like, not how big they are, like how extensive, how far away things are before they get sucked in or whatever. But we're talking about what mass do they have? How many solar masses? How many Jupiter masses for maybe really small black holes? Mostly we measure those in solar masses. But yeah, so that's just a little bit of measuring things. I know there's a lot more in there to unpack, and I don't know, maybe I'll do a deep dive into nebulae or something if I figure out those at some point. But in the meantime, that was just our little stroll around our celestial neighborhood. Tune in next week for all that you want to know and probably some that you don't want to know about the upcoming eclipse. And yeah, should be a fun thing. And I think if this worked out, we're just going to keep doing this thing where we have Facebook and YouTube all one big happy family, because I kind of enjoyed not struggling with the Facebook tonight. Just a happier astronomer. So thanks so much for tuning in. Thanks for joining me. Comments, questions, always appreciated. Again, I'm Irene Pease, your friendly neighborhood astronomer. And for visuals tonight, we've been using Stellarium, which you can find at stellarium.org, and OpenSpace, which you can find and download for free at openspaceproject.com. Take care, everyone. Clear skies. Be safe out there. And if you haven't, go get vaccinated.